So let's start. I have to mention two things. First, you all know that last week I got some sort of death threats that if I continue topos theory, there will be some consequences. So I have to change the course of the course. So I guess the right way to do it is this. So let's just complete this sheaf theory because it is just the minimum thing that we need at least. And also we are in the middle of sheaf theory. So not really in the middle, close to the end. So let's just complete that. Then I move to logic, use this sheaf construction to prove some independence from some theories. And then we can come back. I don't know, we can just arrange something in summer or in the next semester or something, just to continue the rest of topos theory and the rest of the constructions, plus, of course, the other independence results. This is the first thing. The second thing is that I did a mistake and I have to just correct it. So, and the mistake is in the definition of the dense coverage, right? So we had some dense coverage, and the dense coverage was that, let's say, JD of A. So something is, some family, say, is covering for A, and this is my definition. If for any map B to A, it factors through one of the elements, right? So any map factors through these guys. So that's wrong. So the right way is this. So, right? So something is just a covering family. If any other map, any map here, for any other map, some map here factors through that map, right?
Changing the definition of a particular coverage? Or
yes. No. One coverage, that's called the dense coverage, right? So the definition should be this, right? With the arrow in this direction, not the other one. That was my mistake. And then if you remember, we had a baby version of that, right? Over, say, some. Yes. So a family of morphisms to A is called a covering family in this coverage. If for any G, there exists a map from some of the AIs to B such that the composition is the map in the cover.
That's
the dense coverage.
The dense coverage.
JD. That's J.
You're defining a particular property of coverage.
No. I'm introducing one specific coverage, right? To specify that, I have to say that what are the covering families for any A, okay. And I'm saying that some family is a covering family if it has the following property, and the property is that for any G, there exists a map such that you.
Okay. So you're treating all those.
Yes.
And this is coverage.
Yes. So that is just a more complex, more morphism-based version of the one that we had before, if you remember, right? So we had that tree-like thing, and then I said that one coverage over this tree is something like that when you pick some element like this, then all the minimal elements, so the order is in this way, so these are less than these. So all the minimal elements is a covering for this. So to cover this, I need all these 4, here just 2, say if I have this, then here just these 3, etc., right? So this is exactly this coverage without any morphism, simply because So here I'm saying that so if you read it like it is just some elements less than A, such that any other element that is less than A is actually greater than one of these guys. So technically I'm saying that these guys are the minimal elements below A. Right? Okay, so let's continue then. What we had. If you remember, and I'm sure that you remember that we said that this guy is a topos. I said that I didn't like it because there are three reasons. So let's say that I said I have a logical reason, I have geometric reason, I have algebraic reason that I don't like this because it is not generalized enough. So this means that I don't have any general machine to make classical toposes, right? Because toposes are just usually intuitionistic, and this guy sometimes it is intuitionistic. Sometimes, if for instance C is just the group G, it is just classical, but it is not generalized enough, right? So I want a very powerful machine to construct more and more classical toposes, of course, for the sake of independence. So the other was geometric. So the problem is that if you read any object here as some sort of generalized space, then we have generalized space, we have some maps from simple spaces to the generalized space. But usually in geometry, we are interested in local maps, not just any map, right? So you have to change your setting to appreciate this locality. And we did it. Actually, we solved this using sheaves, right? So if you move from this to, say, the category of sheaves, and this category is just the category of all sheaves as objects, not all pre-sheaves, just sheaves objects, and any morphism as morphism here. So it is just a full subcategory, right? So I'm just restricting my objects. So if you restrict yourself to this category, this is just subcategory of that, then simply you are saying that I'm working with local, with spaces, general spaces and local maps, right? And J is there just to formalize some sort of union, and then the sheaf condition is there just to say that everything is local. And we don't know what is this problem, right? So let's first start to show that actually using sheaves and coverages, I can solve the other two problems, right? So sheaves are the answer to all the problems that I have. First, I have to say that what is my algebraic problem, right? So the algebraic problem is just easy to state.
Or maybe just its notation. It's using SH.
Yes.
CJ.
CJ.
This is the family of.
It's a category. The objects are all sheaves with respect to the site CJ, right?
Particular. Oh, it's science CJ.
Yes. And then what are the morphisms? So if I have two sheaves, right? So in particular, they are pre-sheaves. So just use all the natural transformations between them for all maps there, right? So map-wise, it does not change from there. Okay, what's the algebraic problem? The algebraic problem is this. So if you remember, we had this, that set to the C opposite is just a free co-completion of C, right? So you kind of freely, in a formal way, you are adding all the possible co-limits, right? We had this. So in comparison, it is something like, so going from C to set to the C opposite, it is something like going from, I don't know, some set of generators to, say, the free ring of it, or free group, or free module, or whatever, right? So it's just a free construction. And the problem, the algebraic problem is exactly this. It is just a free thing, right? Being free is good because you can work with it just easily, but it is at the same time very bad because it is very restrictive, right? So usually we are interested in all rings, not just free rings, all modules, not just free modules, all groups, not just free groups, right? So you have some generators, you construct the free thing, but also at the same time, you do quotient over some relations, right? And then you have a robust family. So what I have to do then is that I have to do some sort of quotient of this guy over something, right? And then maybe I have a generalized, well-behaved family of things, right? So how to do the quotient then? That is the question. How okay, so first, quotient over what, right? So I need some relations, right? So what are the relations here? So you say that, okay, I have a ring, so let's write some polynomials because this is just what I can generate based on the generators and put equality between two of them. Like what? Something like this, right? You write some relations, algebraic relations based on the things, and then you want to quotient over. So here I have my polynomials are colimits, right? So therefore, the reasonable thing to quotient over is that I have, say, two families of colimits. So colimit of some family, say, equals to, in some sense, let's say, to colimit of another family. Right? Some equations between or isomorphism between colimits. I have to quotient over this, right? The question is how then? So first I can simplify this to say that always do quotient over something like co-limit of AI is A. So pick just A here, simply because always I can add one new generator and then say that A equals this and A equals that, right? So that's just enough to work with this, right? But the point is that after the simplification, simply I don't know how to construct something like this. So in what sense I have to do the quotient? And so usually when you do your quotient in algebra, let's say in that ring theoretic case, you do just a simple thing, right? So you pick your relations, you expand your relation to the smallest possible congruous relation, right? And then do the quotient, and then you inherit all the algebraic structure, and then blah, blah. So here it is just a mess, right? Because I have morphisms, I have co-limits, big co-limits. I cannot just handle that. I cannot just make some sort of reasonable equivalence. And also I have to respect the morphisms, right? So that's just a mess. But there's a trick to do that, and the trick is this. Maybe I have to explain then first the simplest case. Why not, right? So let's say that we are in the propositional case. So I have a poset, and then instead of set to C opposite, I have 2 to P opposite, and there is a map, and this map is some sort of Yoneda type embedding that maps any elements here just to downset A. So these guys are just downsets of P. And you map any A to downset corresponding to A. It is just embedding, etc. And this guy is just a free co-compilation of P, right? So now I want to do some sort of, so you can read anything here formally as something like that I have a family A1, A2, A3, and the whole thing, yeah, this guy is just a poset, right? And the poset is just a poset of all downsets. Because they are order preserving maps from the opposite of P to 0, 1. Right? So if you forget the opposite, they are just order preserving things, and they are just offsets. So therefore downsets. So that pre-sheaves is just the set theoretical, more stuffed version of downsets. So you can and you can prove that this guy is just the Frico completion of P, right? Meaning that any element here is simply just, you can think of it as some sort of formal disjunction or joins between elements here, some big one, right? But formally it is just a set of everything less than these guys, right? So whatever. So what I'm saying is that, okay, let's say that I have some P, I construct a free co-compilation, but now I want to do some quotient over some relation. And what is the relation here? It is something like A or B is C, right? And A, B, C are elements here. So these are generators. This is some relation written based on just a join that I'm working with, right? And then I want to somehow construct this guy. The good thing is that in the order theory, we know how to do this, and it is just very simple. So you restrict yourself from all downsets to all downsets respecting the relations, meaning that so you have a downset D. Respecting simply means that if D has A and if D has B, then D has C and vice versa, right? Yes. Yes. Right? You can read it like this, that any D, any downset is just a map, right? To 0, 1. And what I'm saying is that D of A or B equals to D of C, meaning that C is in D if and only if A or B is in D, and A or B is in D because it's a downset. Simply it means that both of them are, right? It implies, but anyway. Is it? Or I'm just saying nonsense. If A or no, that's not enough. Sorry. So I mean this. I mean this. Let's not just open it, right? Of course, I have to prove that this is really the quotient, right? Meaning that so if what is the meaning of quotient? It means that if I have, of course, I can go from P to the P opposite. This is just a co-compilation. And then I have to prove that for any other Q, in this case, yes. Yes. So what does it mean to have a quotient? It simply means that so you have just the embedding and which is this. And then for any other Q that is also complete, and for any other map F such that F of A equals to F of AB equals to F of C, then you can have some unique map. Yes. What does it mean to have just a quotient, right? Yes. What is the quotient? Let's say that I have some poset and I want to. Yes. Which one? This? On the right, this one. It is f of A or B, say. F of,
I don't understand what
okay. What I'm doing is this. So first I'm saying that I have just a post, right? And this is just a free co-completion. And what does it mean to be a free co-completion? This, right? No. This is the construction of the free co-completion, right?
Well, you said that the pre-sheet is the pre.
Yes, but being free co-completion has a meaning. And the meaning is this, right? That this guy is a free co-completion, right? In the following sense, that you can go from this to that, and for any other complete poset, and any map, of course, order preserving, you can induce a unique map, say, such that it preserves all possible joints.
I mean, it would be helpful if you said what D is in the picture down there. Another concrete example,
Yes.
D.
Which map? D is just an element here. D is something like from P to 0, 1. It should be an element there. Yes. Is it fine? No.
No, in the sense that you were talking about this free co-completion as though it was some kind of algebraic notion,
Yes.
and now you're drawing a picture that looks like it comes from the topos theory. So, should we have seen the definition of free co-completion? We
Yes.
saw the definition of
Yes.
a
Yeah, we saw it, right? So, okay, just for a moment, forget about these things, right? So, I am saying that the problem is that this guy is a free co-completion, right? And it is free and this is bad. What is free co-completion, right? Yeah. So if I define free co-completion just without anything related to topos theory, that should be fine, right?
well, no, but I thought you appealed to something like these diagrams and said this is the general case of taking these objects together and so.
That is one of the interpretation, yes, right? This is the geometric interpretation. But at the same time, this category has some sort of algebraic characterization. And the algebraic characterization is that this guy is just a free co-completion of C. The question is that what does it mean to be a free co-completion, really?
Okay, is this picture now algebra? It was before it was.
Yes, everything is algebra here.
Maybe I don't know the difference between algebra and category theory.
Algebra is some sort of
Well,
attitude, really.
I don't understand why.
Okay, so what I'm doing? First,
Seems like you're trying to justify something from the algebra point of view.
yes. So from the algebraic point of view, I am saying that let's say that we are doing ring theory, right? So if we are doing ring theory, that is not enough, right?
Okay, I understood that.
And quotient is good. Okay. So then the question is that in my just forget about this order. Just in category theory, if this is my C, the generators, what is my free ring? What is the corresponding free ring there?
You said it was this fish.
Yes. But then in what sense? Because when I say that I have a free ring, it has a property that make it free, right? What is the property? Because I cannot just pick a ring and say that you are a free ring from now, right? It should have some freeness property, right? And the freeness property is this. in rings. So let's say that I have, so you have a map from set, say, X, Y, Z, right, to the ring, such that for any other ring, if I have a function, so if I pick three elements, then there is a unique ring homomorphism from this guy to that, right? That is the freeness condition, right? So I'm saying that this guy is free, co-completion, simply because it has this kind of property, right? But in terms of categories and then co-limit preserving things, right? So then the situation is something like this, that I have C, Yoneda goes to set C opposite, and then such that for any other co-limit, co-complete category D, and any functor, there exists a unique opto-isomorphism F hat, such that it commutes and it preserves all possible co-limits, right?
So showing that, starting from the point of view of algebra, this thing is a frequency, it actually is a frequency.
Yes.
Okay.
Right? So this is just a definition of something to be just a free co-completion. The point is that this guy is actually the free co-completion. So this is the construction of the free co-completion. Right? So, okay, now I have my free thing. The bad thing is that I have to quotient. And then therefore it means that I have to quotient to some equalities between go limits here, and I don't know how to do it. Right? And if I want to make it short, say, maybe I can just say that how to do it without bothering motivation. So that's the thing. So let's say that I have some equality between some co-limits, and then I want to quotient over. And here is the construction. The construction is this, that you have, you restrict yourself, right? You restrict, so you want to construct this, right? Say, quotient to co-limit of some AIs is A, right? Say this. How to construct that?
It's be a set of restrictions or just one?
Just let's say for now one, right? But it can be just many. Restrict yourself to functors. So I'm just going for subcategory of this, such that if respect that guy, meaning that since f is just order, it's just contravariant, so it means that the limit of f i's is f a and I, right? If you restrict yourself to these guys, then that's fine. You can see that you are actually constructing the quotient, right? I have to define what I mean by quotient, right? Again, in algebraic abstract sense.
And you have to show this as a.
Yes. Of course, it's category, right? Because I'm just restricting, you know, objects, and the morphisms are there, so it's a category. But I have to show that it is really the quotient, right? Because again, quotient has some sort of specific meaning, right? So let's say that now we are here again, and then I want to find the quotient this, x squared is y 0, right? What does it mean that I have this quotient? It means that first, I have the map, for any map x, y, z to some r, such that f of x, f of z is, let's say, f of y squared, right? Then there should be just a unique f tilde, such that blah, blah. That is the definition of the quotient, right? It is the best between all the rings that you have this equality. right? And what I'm saying is that, yes, this guy is actually that category, but I won't show that. The point is that what does it mean to have such a condition, right? So this condition, if you think about it, is simply saying that, so what does it mean? This means that I have A, and I have some AIs here as some sort of diagram, right, over A. And then I'm saying that just pick some F's that respect this diagram, meaning that I have F of A and F of AIs, and F is contravariant, so I have this. And then I expect F of A to be just the limit, right, of these guys. So this is just a Sheaves condition. If you pick the right colimits, right? The Sheaves condition. Why? Because let's say that I have some cover. A cover is something like this, right? But I also need, say, let's say I have 3, I have 2, 3, and then I have all the possible cones here, and between these two, so all of them, right? Whatever. And then this is your colimit thing. So I'm saying that the condition here is that the colimit of this part is A, right? And if you apply your F to it and check the condition, simply you are saying that F of A is just the limit of F of A1, A2, A3, and all the maps F of B, D, whatever here. So let's make it F long. So what is it? F of B, F of D, F of C, F of A1, F of A2, F of A3, these maps, and say these things. Maybe I'm wrong, but who cares, right? So what I'm saying is that just work with some F's with this property, right? That this is limit. And if it is limit, then it means that any element here is just uniquely determined based on 3 elements here, 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 such that you have these conditions, right? So I am saying that F is a sheaf.
Why B, D, and C here? Are they doing sort of the same job as A?
AIs, yes. So my point is that when you do quotient, you write some colimit, and then you restrict yourself to the F that preserves. So let's now focus on these kind of colimits, right? Because I can pick my colimit, right?
The colimit there is A.
You have to have just a co-cone, not just one element, right? So you have A, some object, and some diagram over it, right? This is just a diagram of AIs. So I have 3 things, and
Colimit. You have some objects, and then you have arrows going A.
exactly.
I don't remember the internal structure.
No. So that is just a co-product. So let's say that the colimit is this, right? So you have some category, right? Some diagram. So let's say something like, of course, it is possible to have this, but it is also possible to have this, whatever. And then you say that, okay, let's just compute the colimit, meaning that there is some element, say colimit C, and some co-cone, such that it respects all the commutation that you want, and it is just the best one, the least one. So now what I'm saying is this. So here, right, you write, this means that you have just some sort of cone.
But does AI also? do-
Yes,
Ah. okay.
Yes,
You
yes.
could- You said you could say.
Yes,
A4,
then-
5, and 6.
yes, yes.
Oh,
It's my bad,
Okay, fine.
right? So if you restrict yourself to these diagrams, then the condition that f maps this diagram to a limit is what? Is the Sheaf condition. This is what I'm saying. If this guy is your coverage, and if you have all possible, uh, intersections, if you like.
So the chief condition is about coverages of A.
Yes,
In this case, it's A1, A2, and A3.
yes.
But it's this thing about.
Let's say that you have just one covering family, right?
The condition is that you have B to A and covering family of B, then you can make some commutative, you can make some squares.
Yes.
So what is B here?
Let's start just with one covering family, right? Right? Then add all possible B's and all possible maps, right? Between any two of these guys, such that these things come in. Add all of them. No, I'm doing nothing, but I'm just adding, I'm constructing one diagram, right? Just add everything to it. And then you have a very big diagram, right? And not just one B, many, right? So then what I'm saying is that if the condition that you have here is this condition, that co-limit of this diagram is A, right? Then I have to work with F's that respect this diagram, meaning that it maps the diagram to a limit diagram, right? And then it means that f of A is the limit of this diagram. This is just a sheaf condition for F. This is what I'm saying.
I understood sheaf condition as being a condition on a category and a covering.
Yes. Yes, that is a covering family.
You said sheaf condition for F.
Of course, you write a sheaf condition for some covering families and some functor, right? You check the sheaf condition for F. Some pre-sheaves, some Fs have the pre-sheaf, have the sheaf condition or not, right? Yeah.
F is a function.
F is a functor like this. Where is it?
Can you just say what you mean by sheaf condition?
Yes. So what's a sheaf condition? So the sheaf condition says that if you have a covering family like AI,
Well, no.
Okay.
What is it condition on? What has its condition on?
so for any one covering family, say,
Yeah.
for any A and one covering family of it, and one F, right? You said that for that covering family, F satisfies the sheaf condition when you have the definition, right?
So where's B?
What's B? Which B?
The sheaf condition I remember is about B and an arrow to A.
I may change the name, but I don't know what should be the B.
Well, at some point, that's a definition.
Yeah.
It says that something is a covering. I'm mixing up sheaves and covering family. You have the definition of the covering family, and then you have an arrow.
Ah,
to
yes. So
A, and
in
covering is B, then you can make it to do something.
yes, in the definition of the coverage, we have some B.
So that's the definition of a J.
Yes.
Okay.
What is a coverage? Then I said that, yes. What is a sheaf condition for a given coverage? Right. So what is the sheaf condition? I have just a covering, right? No? Okay, so you have a coverage, right?
Is the sheaf condition a property or something?
Of course.
Oh,
Being a sheaf is a property of F.
I thought it was a property of a pair of a category and a carbon.
And it could not be, right?
I don't,
Now, if you have just, so you mean a site, then?
yes.
If I have a site, then what is a sheaf?
Uh, I thought-
No. No. The site is just the data of the coverage and the category and nothing else. Then you have some functors, right? Like this, that we call pre-sheaves. Right?
Oh, okay, each of them is a sheaf. Right.
Yes.
Right.
And then some of these pre-sheaves are sheaves when they have that sheaf condition.
Okay.
Right? So now what I'm saying is this, that yes. So now we are here, why not? So let's say that F is just a functor, and when I say that F is a sheaf, when I have the following property. So whenever I have A, some object in C, and a covering family, let's say A1 up to AN, say, right? F1 up to Fn. And of course, it is covering according to J, right? Meaning that this family is just in J of A. Then for any A, for any covering family, you have to have the following thing for your F to be a sheaf. If I have just a family of, say, Xi, in my case, I1 up to 1 to N, but it can be just in a set I. So such that any Xi is in F AI. So in F of these guys, I pick just one Xi, such that it is compatible, meaning that for any AI, AJ, A, maybe this is your B, B, FI, FJ, GH. For any commutative diagram like this, for any two guys here, two maps between them, two other maps, such that I have the commutativity, then F of G mapping F of AI to F of B maps Xi to F of H Xj, right? So this is just a definition of being a compatible family, right? This for this fixed given covering family of fixed A, this family is called a compatible family when I have this property. And then the sheaf condition for this one, for this specific covering family, it says that there for any compatible family, there exists a unique X in F of A here, such that F of Fi of this X is Xi for any I. Right?
No, you gave us a clear definition. I was completely mixed up.
So that is my sheaf condition, right? So what I'm saying here is simply that if you start with a covering family, and if you add all these B's, but all of them to your diagram, right? Then you have just a big diagram. Saying that F respects this diagram in the sense that F of this is F of A is just the limit of the others is simply nothing but just a sheaf condition, right? Being a limit means that so pick just three elements. such that you have the commutativity. So then I have just a compatible family. A compatible family comes from just one x from f of a, right? So the upshot is that if you start with some coverage and then you construct these guys, and then you axiomatize your relations as these relations, which seems very specific, then your quotient is nothing but the category of sheaves. So the category of sheaves then is just some sort of quotient, right?
Taking, construct the correct thing and taking the quotient back.
No, I have to show that this is really the quotient, meaning that it has that universal property. But I don't care for now.
Okay, but what do you quotient back?
By some relations, right? Some equations between colimits, say.
You haven't said exactly which one.
It depends, right? You can choose. My point is that if you have the coverage J, and if your relations are exactly these relations, that the co-limit of this is that for any covering family. What do you mean?
Well, you're saying that there is a certain set of relations.
Exactly.
Quotient back,
You get the sheaves. Yes.
but it's not clear to me whether you actually specify what that family is.
Yeah, I did it kind of informally, right?
The thing about this thing going to square, the thing that looks like the definition, but it's not written down there. It's a thing with these.
It's something like this, right? So what should I put in my relations? I pick just one covering family for any A. I add all possible, you know, the things, and then the condition is that the co-limit of this guy is A. And I have to write for any covering family for any A, and it is just a huge family of relations, and then quotient over those relations, I get sheaves. Okay, but therefore the category of sheaves is just some sort of quotient. But it doesn't solve my problem because I want not just some quotients, but maybe all quotients, right? The point is that one can show that any good quotient, and there is some formal sense of it, comes from one of these guys, right? And good quotient, let me just say that there is some sort of notion of good quotient, right? There are some quotients that are just reasonable, and then any reasonable quotient, you can rewrite everything to say that actually it is a quotient over the relations of this sort. So when you work with sheaves, you are working with all possible good quotients, say.
But surely there's a unique quotient over relation, that's all.
What do I need?
Isn't there just one quotient? Are you saying all quotients? All quotients
Yeah,
are the same?
for different J's, I have different quotients, right?
But you're saying that for each J, there's only one effectively.
Yes,
good quotient.
yes, yes, of course, yes.
And you see, so it's notations, you vector set the C of by calling it AI.
Yeah.
So is this one fixed set or category of AIs or for all these? You say these are sheaves. So you consider particular
Yes.
element or
Yes. So that I'm saying two things. One, for any coverage J, you can come up with some specific, really very specific like this. Exactly. Relations, and then for those relations, the quotient is just sheaves. But the second thing that I'm saying is that it is not that restrictive, meaning that there is some sort of good universal notion of good quotients, and then one can show that these quotients are all good quotients. So by working with sheaves, you get all possible good quotients.
and the category of sheaves is category of all these quotients or
No.
One.
So category of sheaves is this for any fixed C and J. This is just a category of, say, sheaves with respect to that site. And then if you change your C and J, you get many categories with this construction. Any category of that sort is a category of sheaves over some site. Right?
Sorry about the question. It's not that you fix a J and I give you some quotient, but it might be that. But you're saying that if you take the set CR
Yeah.
and any good quotients,
Yeah.
it'll give you the sheet with respect to some J.
Yes.
There's some kind of matching between good quotients and
Exactly. There is one-to-one correspondence between them. Okay. So let's do something easier. The easier thing is just the other problem, the logical problem. So how to solve the logical problem? Again, using sheaves. The idea is this. So first I have to interpret what do I mean by set to the C opposite, right? So when we didn't have our opposite, right? I said that you can read these guys as variable sets. So read your C. So maybe C is just the pole set order. So you have something like this, right? And then this is your structure of time. And then you read any functor here as a set that varies over time. And then, of course, it is just intuitionistic thing because, you know, over time you construct more and more things, right? And of course, it is not classical. So first, when I want to do everything classically, I have to find some sort of interpretation of set to the C, right? And it's better to just avoid any kind of time because, you know, classical mathematics is timeless. The idea is that read C not as the category of time, but as the category of, say, partial knowledge, right? Partial information. And then when I go up, I have more and more and more information, right? And then the variable set is that you construct things at each stage based on the knowledge that you have, right? That's good, except that not all variable sets are acceptable, really. What do I mean? I mean that let's say that I'm a classical mathematician and this is just the knowledge that I have. And then at each stage, I construct whatever I can construct, right? And then we are here. And this possible fork means that at this point, I don't know if, say, the Goldbach conjecture is true or false. And here it is true. And here it is false. These are all possibilities that I have, right? And let's say that if it is true, I know how to construct the thing that I want. If it is false, also I know how to do it, right? Then it's fair to say that I have to know it already here, right? That is just the classical reasoning. If I know for both of the situations, I knew it, even without it, right? It is something like that we had before. If I can prove something from P, and if I can prove it from negation P, then I can prove it, really, right? This is what I'm saying. So if your constructions are just classical constructions, you have some sort of backward condition that if you have one node and all possible end elements, these are just complete realities, right? So you know the value of everything. There is no fork. Everything is just done. So if you know the construction for all the things here, then you know the construction here, right? It's like that it can be complex, right? So this and then say this, and then P negation Q, right? So that is a sheaf condition, right? Because what I'm saying is this: if I know, so let's say that my variable set, let's say that this is my P, right? And this is my variable set. To each node, I assign some set. And then what I'm saying is this, that if I have an element here, an element there, so let's say that these are, say, this is A, this is B, this is C. So if I have some X in f of B and some Y in f of C, right? Then there should be just a unique construction, say Z, in f of A, such that if these are, so, just, because these are just one morphs, but let's call them FG, then f of Z is, what is it, X, and f of G of Z is Y, right? So that's just a formal version of the thing that this is just the construction. F is a construction of sets over time. I'm saying that if I have some element here and some element there, and there is no compatibility condition because there is nothing above them, they should come from one constructed element before, right? Because this is the construction according to, say, P, the other for negation P. And of course, then I have to say that without knowing P or negation P, in this stage, I should have known the construction, right? And it should be, of course, unique, right? So what I'm saying is actually this, that
What you're describing is a condition on a functor.
yes,
Okay. So the functor may or may not satisfy the following condition.
exactly.
That for all x and y, there's a unique set with these functions.
Yes. That's too much, but it is what it is, right?
So this is something like there's a z in f of a which gives rise in sometimes covariant way to x and y.
Yes.
Oh.
Yes.
Okay.
Yes.
Does this condition is the name?
Yes, it's a sheaf condition. It is a sheaf condition if I say that this is a cover for that guy, and since there is nothing above, so that is just simply the sheaf condition, right? So what I'm saying is that at least for this poset, if you use that coverage of using, just all the minimal elements as a cover for something, then it seems that sheaves somehow are the classical variable constructions, right?
Well, so why is it classical? Do you think of f as associating each thing in your tree with some object?
Yes. Some sets. Yes.
And you're saying something like z should be somehow independent of the.
No, what I'm saying is this, that, okay, yes, at each point, I'm constructing some things, right? Okay. And then when I grow over time, it preserves, of course. But then what I'm saying is this, that why do we, okay, what are these points really? These points are partial information that you have, right? Some sort of partial assignment, say. And then when you are here, right, these are all possibilities after your point, right? If you know how to construct something here and there, you have to know it beforehand at this stage, right?
It's like a classical logic.
Yes. So let's say that I say that if I prove something, right? I say that if, let's assume that I have the Goldbach conjecture, then I construct something. And then I say that let's assume that Goldbach conjecture is false. I construct something else. right? Then one can say that, okay, regardless of the Goldbach conjecture, always I know how to construct the thing, either this way or that way, right? Why not?
Well, if you're talking about classical logic, why are you emphasizing knowing how to construct something?
Because you can't. Okay, so you sometimes you prove things, but sometimes you really construct things, right? So let's say that you want to construct some sort of assignment, some sort of ring, whatever, right? You do some construction, and in this case and in that case, right?
Well, maybe can I say it this way? At point A,
Yes,
you say my construction will depend on whether the Goldbach conjecture is true or not,
yes,
and then that's your construction.
yes.
And then
So my
later
X
on-
is the construction.
later on, the point no, so that is it.
Yes. Yeah, Z is the construction here, X is here, Y is there. Right.
This Z,
Yes,
maybe your construction is different things depending on the Goldbach conjecture being true.
yes. But I
But
just
you haven't decided whether it's true or not yet.
because I didn't know,
You
say.
don't know. And then if you go further up the picture, then you know whether it's true.
Yes. But if I can construct things in the whole cover, in all possibilities, after my possibility here, then I can say that I knew it here. Right? So it is just the okay, so maybe you can just think of the truth value, not construction, right? So say that this X is just a truth value. It means that something is true. And this means that something is true here. So if it is true for P or negation P, then it is true without knowing the knowledge for P. So, okay, so what is the more generalized version of this? One could say that, okay, so if I have C, what is the coverage that is somehow close to this coverage, right? That you cover all possibilities in the future, all ends possibilities in the future. And then the shift condition says that if you have the knowledge there, you have the knowledge below. So that is just a dense coverage that I said at the beginning, right? So the dense coverage is this. It says that some things, right? A. So this is just a cover for A. Read it as these possibilities are all possibilities eventually, right? Or it's like that this is A1, A2, A1, 2, 3, 3, right? But here I have no morphism, just at most one morphism. But there I have some morphism. So up to morphisms, it should be the ultimate possibility, right? So these are all possibilities, meaning that if I have another possibility, right, it must be factored like this, right? So this is another possibility, but it is not some independent possibility. It is actually this possibility, but you forget some information, right? It's like this, that so this is a cover, right, of this. So if you have some element like this, right, then that guy must be what? So this is my G, then everything above there should be something above this. That's yes. So it means that there is some element above this, like this, that is also above that. Right? Am I right? Yes. Right? So what I'm saying is that if we work with this dense coverage over any C, then the sheaves for this dense coverage may have some relation with classical logic, right? Because it simply says that if you have some construction, eventually then you have it now. But if it is for all possibilities. And it is actually true. We will see it later, but if I work with sheaves with this dense topology, right? There is one dense topology in NEC. So this is a topos like any other sheaf category, but it's a Boolean topos, meaning that for any object X, the sub X is a Boolean algebra, right? And this is what we kind of expected. So that solves the other problem that I had, right? The class.
This is the proposition that we should write down for the understanding the logical implications of sheaves.
Yes.
Can you say it again?
The proposition, maybe I can write it even, right? So there. The topos, we don't know it is a topos, but later we will see. The topos is the topos is a Boolean, meaning, i.e., for any object X, sub X is a Boolean algebra. Right? So that solves my problem, the logical problem, because I wanted a general, very general machine to construct Boolean toposes and then apply it for independent things. And this says that, okay, pick your whatever C is, just I don't care, right? Pick your C and just add at least this dense topology, but dense coverage, but it is possible to have other coverages, but at least you can work with dense coverage. And then that is a Boolean. Okay, but I have to say another thing.
That's meaningful. It's not perhaps everything to a single point.
Yeah, fair enough. Yes, because it can be just a very bad coverage, right? But it is not. And maybe I can explain it just in the next sentence. The next sentence is this. So there is actually a trick, right? If you are somehow, into the game between intuitionistic and classical logic, you know that there's no need to do that, right? If I have a machine for intuitionistic, right? If I have a way to construct many toposes, each of which has the intrinsic logic, then that's enough. Simply because when you want to interpret your classical theory, first apply the double negation translation, the Gödel's translation. Now it is intuitionistic, then interpret it in any topos. Right? There's no need for this thing. That's a way. That's kind of cheating, but it works. You can show that this is equivalent to that double negation thing. So you can either double negation translate something and then check it in some, say, pre-sheaf topos, or you go to this sheaf topos and work directly with the formulas, right? They are equivalent. So there is a theorem that these two are just the same thing, right?
Sorry, maybe just to remember the logical setup here. So this star
Yeah.
is the
Oh,
complex with respect.
yes, the harmonics into X, and there is some natural order between them, so it's a poset actually. Say
So in the intuition case, this was a Heiting algebra.
yes,
Extra.
that is also Boolean. So every element here has a complement. That's not true.
That is.
That's true for Boolean, not true for Heiting.
And. Oh.
Okay. So, okay, this is just the other problem that I had. And okay, and also it explains why it's not just degenerate, right? Because it is simply just adding double negation, and it does not collapse the whole thing.
But this theorem and the previous one.
Yes.
You can ask, what is the quotient that gives?
Yes, you can write it down like this, but that's just awful. But that okay, it brings me to something very interesting, really, and this is the conceptual thing that I like. One, classicality is some sort of locality, right? So if you are a logician, you work with classical things. This is kind of working with dense coverage. We had coverages because we wanted to work with some local things, right? So it is some sort of geometry, if you like, some sort of locality, being classical. But two is even better. So later we will see that how to prove, say, the independence of axiom of choice or the independence of what? Continuum hypothesis, right, from set theory. You have to construct a model, and this is the model, right? Always, I need a classical model, of course. So I add JD, and I find good C. For each problem, I have to find my C, right? Some C based on partial information somehow. And then this guy just is the counterexample that you want, right? The counter model for these axioms. But there is then something good. One, this is actually equivalent to co-enforcing, right? At least for that continuum hypothesis case. One. Two, now I have some sort of conceptual explanation of the co-enforcing, right? It is just not a technique to construct models.
Well,
It is some sort of canonical one. In what sense? In the following sense. So you go from your C. So C in the co-enforcing is just partial information. It's a poset of partial information. It can be a category of partial information. You can see it just, it is just evident, right? Then you say that, okay, these are my simple spaces. Let's construct all possible spaces or go to the free co-completion, right? It's just a universal construction. It is not just something arbitrary. Go for the universal construction and then do some quotient regarding to this JD, because the quotient makes everything classical, right? You want to, so this is kind of the best way to do everything classical, right? So you want to construct something, you start with some small conditions, generalize it via the co-limit empirical completion to have all possible generalized conditions, if you like. And then it is not classical, right? So do some quotient to make it classical. And there is a canonical, actually, version to do it. There is no magic in co-enforcing. It is just something routine if you think like this.
should we at this point know how to get the constructed model of set theory for this object?
You have to know how to interpret formulas, right? So that's the logic thing that I didn't say, but I will. So
Formulas meaning,
say first order formulas, some language.
but it's not, it's just oh, okay.
Right? Okay. I guess that is, I have time, but should I use it really? Because then it means that I have to start something new, and that's not wise. Maybe.
But,
No, I can't.
give us the outline.
I can. Yes. Yes, I can. Okay, so I guess we need one session or something of that sort, maybe two, to complete this sheaf game, right? I have to show that this sheaf category is a topos. So then we have to see just the limits, its relation with C, that Yoneda thing, I don't know, exponentiation, object classifier, something of that sort. Then that completes the sheaf theory game. Now I introduced one, okay, so not one, but many categories of this sort, right? And then I showed at some point, right? So that these are toposes. So I have a very good family of toposes. So now the question is that how to interpret first order language inside the topos. That is just the next thing. Now, after the district. So we don't do logic in any topos because we don't want it for now, but we can interpret logic inside these topos, right? But okay, so even better because it is not abstract. We have the construction based on sheaves, right? So you can open up actually everything, and there is some control, like the forcing thing. There is some control to control the satisfaction of formulas, and that's good because we want to have some concrete control. And then maybe it takes, I don't know, one session two, something.
So we aim to finish this semester.
Oh, what? Yes, but what? Okay, first, what do you mean by fin? Yes, the first part we can finish in this semester. But when is the end of the semester really?
Our semester ends on, but before.
Yes, okay, maybe we need something also in June, but not much. So
Yes, explanation period, so we can go on.
yes, see, we can go.
But end of
I'm-
by the end of June.
No, we can go on. Yeah,
No,
Pavel is the boss,
oh,
right?
please go
So we
on.
can go on. Okay. Yes. So the thing is that I managed to use really sheaf theory to prove some independence, but and it is not far, right? So we can be there. Then we can have a break, and then after the break we come back and continue the other parts of the posterior. If people want, if people know, okay, they don't want. Yes. See, Pavel is in our side. So. Yes.
So what kind of independence will you be able to show using the current available?
Yes, I guess I can prove the independence of axiom of choice and continuum hypothesis, any kind of forcing things, really. That's just enough to use this machine. Maybe I can also I can prove something intuitionistically because it's also, it needs simply just the pre-sheaves. But yeah, we have enough machine, really.
So independence of axiom of choice.
Yes.
What else do you plan to?
Aha.
do?
Good. So the other things that I want to do is
So you want to be-
then we should continue. Of course, we should continue, right? No, no. The thing, okay, I want to just cover something known classical, right? So the thing is that there are two other constructions. One is somehow one specific case of this, but it's worth to see, right? That one specific case, because it's another construction. It is just a Boolean valued models, right? And it's kind of simple, more logic thing. So But the other one is kind of really new because maybe I can say that these guys are called grothendieck toposes, right? So when I say I have a grothendieck topos, I mean that I have a category that's a topos, and also it has this. It technically is equivalent to one of these, right? You can construct it using some small c and some topology j, not just jd, some j, right? These are some specific family of toposes, right? The grothendieck toposes. And then not all toposes are grothendieck. Because for obvious reasons, right? Like finite set. Finite set is a topos that we saw before, right? But it's just small, so it cannot be something like this because these guys start with set and something, right? They are just big. Or you can restrict yourself to some sort of cardinals, right? Not just finite, and then you get toposes. That's just not very interesting. But there are some examples that are really interesting, right? They are toposes and they are not grothendieck. And one of them is, for instance, effective topos. And I want to cover that simply because first you can prove some computational content like things that you can extract information from proofs. It's no, it is just recursive. It's just recursive, and you can do that, and that's interesting. It's kind of realizability in the usual sense of proof theory, but generalized to say construct models of sets, say. And that's interesting because it is just something very different from forcing, but both of them are some specific case of just toposes. And of course, you can use it to prove things, but there more than independence, what is very important, I guess, is not independence, is the fact that you can construct models of the whole set theory, say, part of, where everything is computable, right? So it is just powerful set theory, like because it is at least a topos, right? With other conditions, but everything is computable in some well-defined sense. And unfortunately, it is not feasible because if you change it to something feasible, like right, then you lose universal machine, and universal machine is very important to construct the whole construction. But it does not mean that the categories there are not that interesting. One should just go and investigate. So these are the other things that I guess.
There is something I think it's the Tenenbaum theorem that Tenen's other model of arithmetic cannot be computed.
Yes.
So that you can construct the set theory.
Yes, but then it means, what does it mean to be computable in the theory, right? So one is that I can encode everything inside, but one is that I have, the track of the encodings, but in some elaborate sense. So there is no real contradiction, really. So there is some sort of trick. Okay, I guess that's enough. Thank you very much. We should continue. But any questions, maybe? Really? Yeah.
About the functions.
Yes.
Like if I understood it correctly, you showed that if I do function like the collimate of some AIs is FA or AI.
Some A, yes.
Then the F satisfying like the F of these functions are sheaves.
Yes.
But then I need like this column portion like for every A or like to get the covering, or how does it work?
Yes. So the point is that let's say that I have some fixed coverage, right? Then I pick all possible covering families, right, for any A, and then I add all possible, say, two maps such that I have the commutativity, add all of them for any pair of these two A's, right? Then you get a very big diagram, right? For any covering family, you get one diagram. right? Then the condition that I want to add is that co-limit of that diagram is A, and I have to add that relation for any covering family, right? So then I get bunch of conditions, some relations, right?
Okay, but I also need to edit for like different X.
Yes, yes,
Yeah, okay.
yes, yes, yeah. For any A, for any covering family, you get just one condition. Yes, yes. Add all of them. True. Yes.
that the group was found, used things that apparently went beyond ZFC.
Yes.
Because it requires some written universes which are categories and categories.
Yes.
So, of course, this concerns some modular form theory or something like that, very, very complicated, but is it possible to explain why one ever may need such objects?
Of course, I have to know Fermat's proof, Fermat's last theorem proof.
Without
Without knowing that, yes. So based on what I know, which is not much, I guess that the thing is that you need the machine of modern algebraic geometry, at least. And the machine, as Grothendieck constructed, is so the main thing there is just the étale cohomology, right? And the étale cohomology is actually cohomology with respect to one specific topos, which is the étale topos. And how to construct that topos? The idea is that you pick one scheme, say one variety, all varieties over that, and then you come up with some sort of coverage, which is the étale coverage, and then you work with sheaves there, etc. Right? The problem is that that category C can be big. The category you start with, it is not small. So to make sense of the whole thing, you need one level of universe at least. And then maybe you iterate things that I don't know, but you get some, at least some levels of universes to have, enough sets. But I guess people think that should not be necessary, right? We can open up everything. And I guess Colin McClarty has one paper actually on that. Colin McClarty, that is not, yes, it's not really needed. Yes.
in fact, there was a lecture by Angus McIntyre,
Yes.
where he claimed that it actually can be done in I sigma 1. So it's well, this nevertheless it is interesting that you can use such strong means to prove something, and then of course
Yes. Exactly. Exactly. Yes. Sure.